Okay. My title presentation of my research is Comparison of Performance of Conventional Control and Adaptive Sliding Mode Controller, that is ASMC, for induction motor drive. I'm Fizatul Aini binti Patakor from Politeknik Merlimau, and my co-author, Dr. Zulhisyam Salleh, and also my co-author, Muhammad Hasif bin Aziri. So my outline of presentation, including introduction, literature review, methodology, result and discussion, and also the conclusion. So this research basically based on induction motor drive. Induction motor basically are used in many applications in especially in what we say in industrial application because of their rugged reliability and also relatively low cost compared to other motors such as DC motor. However, despite their advantages, induction motor require a control scheme due to their highly non-linear dynamic structure and intense dynamic interaction. This is need for a robustness against electrical fault, load disturbance, speed variation, and also parameter uncertainty. So this research actually focused into design a robust induction motor drive. This is achieved by employing adaptive sliding mode control algorithm designed to handle the outlined issues just now. So the adaptive sliding mode control improve upon conventional robust sliding mode control by integrating adaptive switching gain control strategy and discontinuous sigmoid function to eliminate undesirable chattering phenomenon. This chattering phenomenon actually happen at, or appear in conventional sliding mode control. So limitation, basically induction motor drive is using what we call PI, proportional integral, and also proportional integral derivative control, that is PID. It is commonly used, but it's often non-optimal performance in variable speed position control. So as a solution, therefore, these limitations are solved by intelligent and adaptive control algorithms such as fuzzy logic controller, sliding mode controller, and also artificial intelligent neural network ANN control. Fuzzy logic controller provide dynamic performance and robustness to the parameter variation. The NNN accommodate arbitrary complexity and non-linearity. So these the SMC excel in order system order rejection and distribution rejection. So in order to deal with the robustness, this study focused on the SMC application in induction motor drive. So basically, there is conventional sliding mode controller. So this sliding mode controller have chattering phenomenon due to large switching gain in the equation itself, in the SMC itself. So this is undesirable effect caused by external load disturbance and parameter variation. So in this classical SMC are technically prompt with integral SMC. So modification of control function to address the chattering, transformation from discontinuous to continuous control function. So basically the classical conventional SMC using discontinuous function. So this integral sliding mode control will use the continuous control function. So the proposed adaptive switching gain control strategy, this research also introduced adaptive switching gain control strategy, which aim to overcoming instability and achieving smoothness in control performance. And also introduction a new algorithm with modified classical sliding mode control with variable gain dependent on the system state to reduce chattering and enhance its robustness. So this is the control system employed in direct field-oriented control. This indirect IFOC, indirect field-oriented control, widely used method in controlling induction motor. This is the speed control where the SMC, sliding mode control, is implemented in the controller. It's utilized adaptive mode control for speed regulation in ensuring robust performance in varying conditions. Additionally, we have two PI here. Controller, PI current controller are employed in the inner loop. There is outer loop and inner loop. The PI is employed in inner loop. It is to process the error signal of the voltage command, enhancing control accuracy. So basically, this is the conventional sliding mode controller. The equation where this the IQS is the output. This is the IQS is the output from the controller, the IQS, and this is the basically the conventional sliding mode controller output from the speed control. So it is used the signum function, which is 1 to -1 of the signum function. That is what we call its discontinuous function. So in adaptive control, a sliding mode control, we use IQS. This is IQS, which is use sigmoid function. Okay. Whereas the sigmoid function is actually using the arc tangent formula. The control method based on discontinuous function is disposed of the entire operation by implementing fast sigmoid function with arc tangent algorithm. So the modified control algorithm obtain the boundary layer based on the sigmoid function here. So the adaptive switching gain is designed to be proportional to the absolute sigmoid function as mentioned in the formula. So this is the result, simulation study based on the cases for comparative performance on different speed controller with no load. And loaded condition. So we have two conditions, which is no load and loaded condition 0.5 Newton meter. So this table, we have three results here. This is using PI controller, traditional SMC, and also adaptive sliding mode controller. So the table shows the summarize of comparative study of the three speed controller, okay, operating at 1,400 RPM. This is I do the research for two different speed, which is 1,400 RPM. This is the rated speed, and also the lower speed is lower rated speed, 350 RPM. So as induction motor, speed performance are clarified using time domain, specification of delay time domain, delay time, this delay time, rise time, peak time, and also the maximum percentage of overshoot, and also the sampling time. As we can see here, the adaptive sliding mode control demonstrate robust performance with moderate overshoot here. So with moderate overshoot and relatively short settling time under both no load. This is no load and loaded condition. On the other hand, the sliding mode controller exhibit faster response time, but at the cost of higher overshoot and longer settling time. While the proportional integral controller showcase significant overshoot, as we can see here, for both loaded and unloaded condition, but while still achieving acceptable settling time. So next is the clarification of simulation cases for comparative performance on different speed controller with no load and loaded condition, which is 0.5 Newton meter at low rated speed when it is triggered at 2 seconds. So it is the PI, and then the traditional SMC, and also the adaptive sliding mode control. So for cases with no load, the adaptive sliding mode control, we can see that exhibit a rapid rise time here, which is 2.73. Second, modest overshoot at 8.54%, and settling time of 6.14. While the SMC display a similar performance profile with slightly longer rise time. This is longer rise time, 2.81. Okay, second, higher overshoot, 15.85. Okay, and the PI controller, in contrast, demonstrate a longer rise time, 2.87. Okay, and a substantially higher overshoot of 23.23%. So when subject to 0.5 Newton load, all the controller exhibit slightly longer rise time, with the adaptive sliding mode control maintaining the lowest overshoot at 3.66%, and shorter settling time at 6.62. Okay, this finding underscored the influence of load condition on the controller performance, with the adaptive sliding mode controller proving to be favorable choice of rapid and stable control for lower rated speed at 350 RPM. So as we can see here, it is actually the hardware implementation for the sliding mode controller. So we have here, this is the hardware experimental setup, but the hardware implementation only cover on the adaptive sliding mode controller for 3 conditions. So for speed 1,400 RPM for high rated speed, and lower rated speed 350 RPM. So we do this experimental based on 3 different load conditions, which is 0.125 Newton meter, 0.25 Newton meter, and 0.5 Newton meter. So this is the result based on experimental of the adaptive sliding mode controller. Okay, so I classify it into cases 1, which is 1,400 RPM, and cases 2 for 350 RPM, where both are tested with 3 different load condition. In case 1, the adaptive sliding mode controller exhibit remarkable performance adaptability to different load conditions, showing rapid rise time, minimal overshoot, and consistently short settling time. As the load increased from 0.125 to 0.5 Newton, the controller maintained its efficiency with negligible deviation in its performance metric, illustrating its robustness across the range of load. So as a conclusion, we can see here in the superior performance, the adaptive sliding mode controller outperform other speed controller in various operating conditions. When we look into consistency across the speed, it's maintained rapid rise time, minimal overshoot, and short settling time at both high speed and also the lower speed. And when we see the robust under load, it is the adaptive sliding mode controller demonstrate recommendable performance even with 0.5 Newton load, showing adaptability and stability. And it is show that the adaptive sliding mode controller ideal for application requiring precise and swift control. Establish it a standout controller in comparative study. So that's all my presentation. So thank you.